recording?
Okay, I started the recording. You can go ahead.
Okay. All right, thank you. So welcome, Michał. Most of you know Michał already, and Michał has been actually a frequent speaker at MOPA already. So today he's here from Warsaw. From Warsaw, Michał?
I mean, I'm sitting at home in Łódź.
Łódź. So today he's talking to us from Łódź, and you see the title. Okay, welcome.
Hello, thanks for the opportunity. It's great to be back at MOPA. And hopefully soon it will be possible to meet at MOPA in person. However, today I will speak remotely, obviously, about model quantifiers, potential infinity, and Yablo sequences. And I will recall what Yablo's paradox or the Yablo paradox is. And after that, I will say a little bit about how to formalize Yablo sentences and whether it's actually paradoxical to have the Yablo sequence or disquotation principles for Yablo sequences in your theory. And I will try to center the talk around the philosophical idea of finitism to get over the paradox and maybe explain it away in some sense. And then I will try to say why a certain approach to finitism that has been around for many years now can be seen as unconvincing from a certain perspective, and why perhaps a convincing version of it is the one that uses a different interpretation of quantifiers that we call a modal interpretation, because we define it in terms of a version of accessibility relation as is defined in semantics of modal logics. But then we see that the potential explanation of the paradox actually disappears, despite the fact that the version of finitism offered by this modal interpretation actually may be seen to be convincing. And afterwards, if time permits, I will sum it up with some remarks concerning semantics and ontology of natural numbers and models of arithmetic. So without further ado, let's get to Yablo's paradox. It consists in analyzing the following infinite sequence of sentences, and it is sometimes called an omega liar or an omega version of the liar paradox. So I first heard it in a version that you have office hours of a professor, and you've got an infinite list of students waiting in front of the office, and every student says that all the guys behind me in this queue are lying. So in a sense, you've got an omega sequence of sentences, and the zero sentence says that for everything with a higher index than mine is false. The first one says everything with a higher index than mine is false, and so on and so forth. So the nth sentence on a list says that for any k greater than n, the kth sentence on the list is actually false. And now to reconstruct the reasoning that seems natural and is done in natural language, the way you ask questions about the sequence is the following. You ask first, can any of the sentences on the list be true? Can it be the case that yk for some k or yn? So suppose that some yn holds. This means that for every j greater than n, yj is actually false. So it doesn't hold. So in particular, this means that n plus first sentence on the list is false, and for any j greater than n plus 1, yj is false as well. But this actually means that for the second part of the conjunction here is exactly the same, is exactly what is being expressed by the n plus first sentence on the list. So yn plus 1 actually holds, but then it means that both yn plus 1 and not yn plus 1 hold, which is a contradiction. So this means that yn cannot hold. But n was arbitrary, so yn is not true for any n. So it's not true that yn unconditionally. But then when you take any n and you say that yn doesn't hold, then it means that for some k greater than n, yk is true. But then you've got some yk that is true. Yes?
You know, so again, I always have to apologize. This is MOPA, so I will rudely sometimes, instead of raising my look. So would it be the same sequence if the word is false was omitted?
So actually not, and this is exactly what I want to say. So the thing is that if you had a crowd that is not so well educated with respect to truth theories and arithmetic, the kind of reasoning that I'm presenting would go through without any questions. And one of the things that you can analyze with respect to the paradox is if you believe that you indeed reach contradiction by doing this reasoning, then it is not trivial what assumptions you actually have to be able to perform this kind of reasoning. And that is exactly what I want to reveal on the next slide. So it will be something perhaps slightly different. So, but
right, thank you.
Yeah. Keeping it now, so then it means that yn wouldn't hold, so you would have that for some k, yk is true, but then you would be able to repeat the reasoning that led us to contradiction. So it also cannot be the case that all yns are false. So it cannot be the case that some yn is true, but it cannot also be the case that some yn is false. So this means that the sequence seems to be paradoxical. And in natural language, when your terms and where expressions of what you reason about are actually quite vague, this perhaps goes through, and you can see and you believe that this is a paradoxical sequence. But there are some background assumptions that we actually used if we are to believe that we actually reached a contradiction. The first one is that we need to assume the so-called uniform disquotation principle for Yablo sequences to be able to perform this reasoning. In some of the slides, I will be sloppy for the sake of smoothness of what is being conveyed, in the sense that we should have, you know, dots and Gödel codes and brackets and everything. I will sometimes omit that whenever this doesn't lead to any confusion. So we here should have uniform disquotation, at least for the Yablo sequences, meaning that if we want to formalize Yablo sequence as a predicate y that denotes that that means that yx means that it is the xth sentence in the Yablo sequence, then we would like to have an assumption that we have to have an assumption that for any x, y of x holds if and only if the formula y of x is actually true. Since if we use local disquotation, that for any particular natural number in a standard omega sequence of natural numbers, if we assume that the nth Yablo sentence is equivalent to the truth of nth Yablo sentence, this will not be enough unless we use omega rule together with Yablo disquotation, where by omega rule I simply mean that we can derive for any x phi of x if we are able to derive phi of n for any standard n. So in order to be able to properly formalize, which I will in some fragments do a little bit later on, the reasoning just presented in the so-called natural language version of the derivation of a contradiction from the analysis of Yablo sequence, you either have to actually have quite strong assumptions concerning the truth predicate, or if you want to keep the assumptions on your truth predicate, I mean, at least the ones for the sentences that you actually deal with, if you want to keep those weak, then you have to have a stronger rule of reasoning to be able to derive this contradiction. And the details to some extent follow. So this, at least in a trailer-wise version, answers the question that it wouldn't be the same if we simply had negations over there. So in a sense, at the very beginning, it is a little bit of cheating to trust natural language when analyzing Yablo sequence. And I will get back to this, but if we buy any of those two choices of assumptions for deriving contradiction from Yablo paradox, one of the things to think about is maybe there are ways to explain the paradox away, and perhaps an idea that a certain version of finitism could somehow rescue us. In a sense, might be useful. So I will, before I get into finitism, I will first tell what I do not get into and what is quite popular in the literature on Yablo's paradox. So the most popular topic concerning Yablo's paradox is whether there is self-reference in those sentences or not. Because I mean, the original idea of Stephen Yablo in 1994 was to present a semantic paradox that doesn't involve self-reference, due to the fact that, I think it was Russell who said that all those paradoxical phenomena and the logical tricks in natural language stem from the fact that they all use self-reference in some way or another. And Stephen Yablo wanted to present the paradox that doesn't involve self-reference. And then there was a big discussion in philosophical logic, also the mathematically informed philosophical logic, whether there is actually self-reference or there isn't. And this is something I don't engage in at all in this talk. But one of the ideas to get out of the paradox is, roughly speaking, to try to come up with a version of finitism in some way. I will try to make it precise with what we mean by finitism in here, in actually two ways at least. But the rough idea is that maybe if in some sense the world is finite, and you can code only finitely many Yablo sentences from your sequence after you formalize it, which will I get into, then the last one is simply vacuously true. I mean, for everything higher than a given index, it definitely it is not true because it doesn't fall under the scope of the truth predicate, for example. So maybe that's an idea. Then we have to make sense of arithmetic in some kind of a formal finitistic setting. And also I need to tell you how to formalize Yablo sentences, but this will not be difficult. And the strategy to formalize finitism is to use the idea that actually it seems to be getting more and more attention from the community of mathematically informed philosophical logic. I mean, we are, I guess, all familiar with the idea of potentialism and this research program in models of arithmetic and in philosophy of models of arithmetic and philosophy of set theory of having potentialist systems. Quite recently, Stuart Shapiro and Øystein Linebo have a couple of papers concerning the revival of the notion of potential infinity. And recently also Hannes Leitgeb has proposed a new potentialist and finitistic semantics for the language of mathematics, for his general positions in philosophy of mathematics. And also what I want to get into details with is the framework that was originally developed by Marcin Mostowski, and what was a trial to explicate the notion of potential infinity and the contrast between potential and actual infinity. So the way to explicate finitism is to use the notion of potential infinity in the first very rough approximation, expressing that there is finitely many things, but there always could be more things. And what we will want to do is actually to make a better sense of this could in the first approximation of finitism. So before we get into that, let me get back to formalization of Yablo sentences. So first of all, we all know that you've got a mature version of the diagonal lemma. If you have a nice theory, meaning that for us in here, you have a first order theory in the language of arithmetic together with the truth predicate, and assume that your theory contains Robinson's arithmetic of, or if you want to have a more powerful theory instead of Q, you can assume elementary arithmetic or whatnot. I mean, the ones that allows you to do Gödel's theorem and stuff. And let's call such a theory nice. And if you have a nice theory, then you have a diagonal lemma for any formula with 2 free variables, and that is enough to be able to prove that you have Yablo formulas. But before that, the dot notation is such that when we quantify over some formula where we have phi of x in the brackets, then we use dot x to mean that for all natural numbers x, the result of substituting a numeral denoting x for a variable free in the formula phi has a given property p. So the dot will sometimes appear here when I show the formalization of the Yablo sentences. So what it means for a formula to be Yablo. So a formula is a Yablo formula with respect to a given theory if this theory is able to prove that for any x, the formula is equivalent to a sentence saying for every w greater than x, the result of substituting blah, blah, blah for in y of w is not true, right? And what I mean by Yablo sentence is a Yablo formula that is of the form y of n, where n is some standard numeral n. And now the theorem proved by Graham Priest in the 90s is that if you have a nice theory, then there are Yablo formulas in this theory, and you simply apply the diagonal lemma because you can diagonalize with respect to the formula that says that for every w greater than x, the substitution of name of w and x in the formula with code y is not true, right? So by the diagonal lemma, you have exactly what you need. So the theory proves that y of x is equivalent to what it needs to be equivalent to. This is just to justify the claim that we are here on safe grounds. But when we enter those safe grounds, then we need to be careful when we ask whether there is actually a contradiction or not in the Yablo sequence. There definitely will be some version of inconsistency when we consider the Yablo sequences. But just to recall, the theory is omega consistent if you have no formula such that your theory is able to disprove every phi of n for all standard n's, but simultaneously it thinks that there is a witness to the formula phi some, but it doesn't know which exactly it is. Otherwise, the theory is omega inconsistent, of course. And what we want to additionally define is the so-called arithmetical disquotation and Diablo disquotation. So arithmetical disquotation is simply the set of sentences that say that phi is true if and only if phi holds for every sentence that is purely arithmetical. And we include that just to be on the safe ground when we consider theories that might be called truth theories. So we use the popular assumption here that a theory that doesn't contain or doesn't prove all the instances of arithmetical disquotation couldn't fairly be called a truth theory. So when you add to your theory arithmetical disquotation, you are safe to speak that you are considering some truth theories. And since obviously right away an arithmetical theory that adds disquotation for all sentences without a stratification and without the restriction to arithmetical language would have an inconsistent theory, here we will consider theories that also have local Yablo disquotation, which is simply set of the same Tarski's biconditionals, but restricted to Yablo sequences, to Yablo sentences, right? So Yablo sentences contain truth predicate. They are not purely arithmetical sentences, but let's add the local versions of Tarski's scheme to our theory to be able to analyze them and to have some assumptions concerning the way that the truth predicate behaves with respect to those sentences. And now a theory PAD is a theory that you get when you add the arithmetical disquotation and Yablo disquotation to PA with the truth predicate. So basically PAT is simply PA in the language containing truth predicate together with the induction scheme for formulas containing truth predicate. And PAD is this theory together with those sets of disquotation schemes. And PAD minus is the same, but you forget about the induction for formulas containing the truth predicate. Okay, so simply PAD is a local disquotation theory of truth for arithmetical sentences and Diablo sentences only. And now the question is whether such a theory is consistent or not, and if it's consistent, is it fully sane? I mean, sorry, I use the technical term because I think there are sane and otherwise models of PA. So, but if it's reasonable in some sense. So, Jeff Ketland proved that PAD is omega inconsistent, but that PAD minus is actually consistent. So additionally, you can prove that PAD is consistent as well. So you have a theory that is consistent, but omega inconsistent only. So in a sense, you cannot derive a contradiction from the mere theory PAD. You would have to add something, and it is actually easy but interesting exercise how you adding omega rule gives you simply the contradiction from the Yablo sentences when analyzing them with those weak local disquotation schemes. Whenever you think that's trivial, then please just tell me. But if not, then I thought it might be interesting to show how it follows that you actually have a consistent theory here. So to prove that PAD minus is consistent, you simply take a non-standard model of PA. Which in this moment justifies why I am even speaking at this seminar about those topics, and then you take a function t of x that gives you a Gödel number of y of x, and by overspill you will find non-standard numbers such that the value of t for the argument b in the model M is equal to c. And you define an interpretation of the truth predicate in the model M. Let's call it S, and let it be the arithmetical theory of the model M together with the number C. Due to the fact that it has the theory of the model, it will satisfy the arithmetical disquotation. And secondly, since you don't have any Yablo sentence for any standard numeral in the interpretation of the truth predicate, but you have one that is non-standard. You have that for any n in omega, the model doesn't satisfy the Yablo sentence y of n, but also for any n there exists an x such greater than n such that y of x is true. So what you have in general is that you have negations of all y of n's, negations of the truth of all y of n's, but also the fact that there exists some x greater than n for all n that are standard. So you actually do satisfy Yablo disquotation by those two. But simultaneously, you can easily see that if we took the uniform Yablo disquotation in here, it would fail in this model. It wouldn't be satisfied if we took the stronger assumption concerning the truth predicate. So it is essential that this is only local disquotation scheme, i.e., restricted to standard natural numbers. And by looking at the easy use of compactness, you can actually also prove that if you add induction to your assumptions, if you add induction with formulas containing the truth predicate, you can still have a model for PAD. And this is the fact that if you take any finite subset of the theory, you put only the last Yablo sentence in the extension of the truth predicate and check that the induction holds, and then apply compactness, and you've got the entire theory satisfiable in some non-standard model of PA. However, interestingly, this is maybe a little bit on the side of the main thread of the talk. It is simultaneously a conservative extension of PA. in the syntactic sense of conservativity. So it doesn't prove new theorems in the purely arithmetical language, where by new we mean new with respect to what is provable while working with Peano arithmetic axioms. So to show that, suppose that we have a statement that PA doesn't prove. This means that PA and negation of phi is consistent. So there is a model that doesn't satisfy phi. It can be non-standard. So then there is an elementary equivalent model M prime such that M prime together with an interpretation of truth in the model M prime satisfies PAD actually. Since this model is elementarily equivalent with respect to the language of arithmetic, so it doesn't satisfy phi, but then it means that PAD cannot prove phi as well. So it means that if PAD proves some sentence in arithmetical language, then PA has to prove it already. Okay, and now what is the way that we get a contradiction if we use the uniform Yablo disquotation? When we take this theory PA with the language of truth and the uniform Yablo disquotation, then by working in this theory, since we know the theory is nice, we know that there exists probably a Yablo formula in it. So by uniform Yablo disquotation, we can actually take out the truth predicate, and by unraveling what y of w means, we can see that it means that for any x, we have that y of x is equivalent to the fact that for every w greater than x, there exists something even greater such that y of z, then there exists some greater z such that y of z is actually true. But then by uniform Yablo disquotation again, this means that for any x, y of x is equivalent to the fact that for any w greater than x, there exists a z greater than w such that y of z. But then it means that y of x is for unconditionally for all x uniformly. For all x is equivalent to there being w greater than x such that y of w holds, and this is already a contradiction when we substitute y of x unraveled by yud again, and this means that our theory is inconsistent. So this shows that if you I mean the assumption that if you want to reason in first order logic without additional infinitary rules, and you think that the formalization of your theory of truth in which you can reason about about objects such as Yablo sentences should prove contradiction, then you have to have at least the assumptions concerning the truth predicate at least this strong. Oh, actually, I said that might be an exercise, but actually with an omega rule, you also have an inconsistent theory. So let me get through it anyway. So by repeating the natural language reasoning to some extent, you can show that y of n cannot hold for all. For all n, you can show within your theory that y of n cannot hold. But then by Yablo disquotation for any n, this means that you can show that y of n doesn't belong to the scope of the truth predicate. And then by applying omega rule, you have the fact that for any x, y of x doesn't fall under the scope of the truth predicate, and in particular, the 23, Yablo 23 is true, which gives you an inconsistent theory right away. Okay, so this shows how the Yablo sequences behave with respect to general formal theories of arithmetic together with the truth predicate, and it means that even if you have theories that prove the existence of Yablo sentences as objects, then it should say that they can still be consistent, not necessarily that they all that they all are. They are omega inconsistent though. And one of the ways to formally obtain a contradiction is to have a uniform Yablo disquotation, or keep local disquotation and add omega rule as a rule of reasoning to your formal system. But this seems to be unsatisfactory, just to say, well, the paradox is not really a paradox because there isn't a contradiction, assuming you've got this or that formal axiomatic theory of truth. It seems that there is something more to it, or at least there can be some philosophically different and formally different as well perspectives to tackle the paradox, or to look at its properties. And to get to them, let's introduce a certain framework that will be directed at trying to explicate the notion of finitism as potential infinity. So we will define the so-called finite model domains, or the FM domains, which were, as far as I know, invented by Marcin Mostowski at the beginning of the century. For formal reasons, we consider the relational version of the arithmetical language, and the FM domain of the standard model of arithmetic will be the set of its finite approximations. So n of n for positive natural numbers, where each n of n is simply consisting of a finite universe containing exactly n elements, so an finite initial segment of natural numbers, and relational interpretations of symbols for addition, multiplication, 0s, and the ordering, where 0 here is simply a predicate, where by restriction to n we mean the formal restriction to the size of the universe. So in here we use the relational language in particular for the case like when we have, for example, n17. If we have 15 and 16, they will simply not be two first arguments of a triple that would belong to the interpretation of addition, right? Whereas in the functional language, we would have to, I don't know, give it a value of 16 or something like that. So in here, they simply won't be under the scope of interpretation, under the scope of the addition predicate. And now what we want to focus on is the so-called SL theory of such an FM domain, where SL stands for sufficiently large. So it will be a kind of a theory of what is true in the limit of such a finite model domain, because we will look at those finite models as points of this FM domain, check what is true in every single one of them, and then consider those sentences that are true in the limit of such an FM domain. So we take a look at those finite points as finite models. We simply apply the standard definition of satisfaction relation in those finite models. And we consider a sentence, arithmetical sentence phi, to be SL true in the FM domain n, or to be true in the limit for the FM domain of natural numbers, or to be true in the limit in natural numbers, if for sufficiently large finite points of the finite domain, it is true at those points, right? So if from some moment on, phi is always true. And yeah, the SL theory of the FM domain of natural numbers, for instance, will be the set of all arithmetical sentences that are SL true in the sense above. So I will not today. I will not give you a lot of properties of those FM domains and of SL theories of FM domains. But yeah, there are at least a couple of works in which this theory is quite developed and quite interesting, I think. So it's also a good idea to get acquainted with with it. What we do here is we enrich the definition of FM domain with an FM domain that contains an interpretation of the truth predicate. So you simply take a family of not only simply finite points being finite models of arithmetic, and I mean the finite initial segments of a model of a standard model of arithmetic, but such that they contain a unique, for each k only one interpretation of the truth predicate, where the intention is that tk is the set of Gödel codes of sentences that are to be considered true at a given point in the FM domain. I mean the ones that can be coded. I mean the ones for which you have codes in this FM domain, right? If you have a point, sorry, not in the but the points in FM domain. So if you have if you have a finite model consisting of 12 elements, then probably you don't have many arithmetical sentences. You don't have many Gödel codes of arithmetical sentences as elements of your FM domains. And a good information about this approach. And I didn't say the most important thing. So this is one of the ways to explicate the notion of potential infinity. So if in the FM domains, all the models that are those points in the FM domain are finite, and they are only finite approximation to this infinite idealization of the structure of natural numbers. But so you evaluate formulas only in those finite models belonging to the FM domain. But what you do with your the potential infinity, you consider what is true in the limit in some sense. So you have all of those finite models, and this means that there can always be more things. So in a computer version of explaining the approach, it is like if you have memory for any kind of combinatorial or computer operations that you want to perform. You always have finite memory. Things are finite in your computational practice, but in the idealized situation, you could always buy up more memory if you need it for some operations. So you always can enlarge your finite model, and you consider as SL true all the things that in the limit would become true. I'm not trying to at once defend philosophically the approach to finitism. I mean, I'm coming to the point at which I explain one or two of the reasons why it might be considered a philosophically not convincing, but that's the way it appeared in the literature with this kind of interpretation. Actually, a good thing about this approach is that important.
Michał,
yes.
Bob has a question.
Yeah. Could I? Maybe I missed something here. So you're picking out one of the TK for each K. Are you assuming any coherence among them? Is there some sort of some SL theory for this system of NK TKs? Because
in a moment I will. In a moment I will, but for the general definition here, not yet. So you know, this FMNT domain doesn't have to be reasonable with respect to the interpretation of the truth predicate at given points and the relation at all. But in a moment, I will impose some restrictions that are exactly the coherence restrictions.
Okay, great.
But before that, things for the pure FM domains and their SL theories, the things concerning arithmetization and formalization are the way we would like them to be. So we still have representability of syntax in the limit. We still have Tarski's theorem on the undefinability of truth in the limit. The diagonal lemma still holds in the limit for the FM domain, and actually you can still prove that you still have Yablo formulas that SL probably exists in a sense. So there exists a formula y of x such that for any domain, still without a restriction yet, for any natural number, it is SL true in the FMN domain that y of n is equivalent to what it is supposed to be equivalent to the fact that for all guys bigger than me, y of x is not true. And now a theorem kind of formalizing the statement that I made at the very beginning, that the last Yablo sentence that we have the Gödel code for in any finite model is vacuously true is true. I mean that if you take any class of finite models such that they SL satisfy AD plus YD, and this is already the coherence restriction, right? That in the limits, I mean that for any arithmetical sentence from some moment on, you've got the fact that this sentence is true if and only if it holds. And if you have the same condition imposed on the Yablo disquotation, then for any natural number, the nth Yablo sentence doesn't SL hold in the class of finite models. And again, as in the previous examples, the arithmetical disquotation is not essential here. It is only here to be sure that what we are discussing are things that can be legitimately called truth theories, so that the interpretation of the truth predicate in the FM domain, in the FMNT domain, behaves coherently, at least with respect to this weak condition of Yablo disquotation. And the reason why this holds, that why this is the case, that yn doesn't hold for any standard n, is that basically the standard natural language argument formalizes easily, so I will not repeat it here. And obviously what is additionally required is that, I mean, we prove here a general statement that for any class of finite models, if they SL satisfy AD plus YD, then something happens. But it might be the case that there is no class of finite models that would SL satisfy AD plus YD, but actually there is an FM domain that satisfies AD and YD in the limit. And the way to obtain such an FM domain is, you, as interpretation of the truth predicate, you take all the existing codes of true arithmetical formulas, right? So this is the way you you guarantee this kind of a coherence. And as I said at the very beginning, you take the code of the last Yablo sentence that actually is that you can still have in the universe of the finite point of your of the given finite point of your FM domain. So there is an FM domain that satisfies YD and YD, and in this domain, y of n doesn't hold for every n. So in a sense, the Yablo sentences are false in the limit, all of them, right? So no paradox. Well, the problem is that maybe the entire approach is not so convincing in the first place. The SL theory of this model of this, I mean, the SL theory of this FM domain is still omega inconsistent, and you can see this even by looking at Yablo sentences. As we said, each particular Yablo sentence shouldn't say is SL fails, but simply SL fails. So fails in the limit, but in each finite point, the last Yablo sentence is always the last that you can have as a code. I mean, the last that you can have as a number of in your finite point is satisfied. So the fact that some Yablo sentence is true still SL holds, because you also have this Yablo disquotation satisfied here, right? So you have that for every n, not y of n, but there exists an x such that y of x always. However, this problem doesn't seem to be a problem with the truth predicate or with Yablo sequences as such, but the fact is that actually, and this reveals one of the problems with the approach, with the approach not even for the language containing the truth predicate, but for the language of arithmetic already. That actually, if you take a look at it, that at every finite point, if you use the standard definition of satisfaction, there is always a maximal element. There is always, I mean, the sentence saying there is an x such that for every y is not greater than x is true in every finite point of the FM domain. However, the fact that 17 is the greatest number or the greatest element, SL fails. I mean, after we are at the 18th point in the FM domain is not true. So for every particular natural number, the sentence saying that n is the greatest number fails in the limit. However, the greatest number exists, not only SL holds actually, but holds at every model. So the entire the FM domain of the standard model is also omega inconsistent. So the way to phrase it is that even if we would like to formalize finitism, it is somehow problematic to have this kind of sentences in our arithmetical theory anyway. But maybe there is a way around it. And this is one of the ideas that we had that I would like to present. So we might want to give justice to this idea contained in the concept of potential infinity, that maybe there are only finitely many objects in the universe, but there always could be more in a sense. But this could be more is in a sense evaluated not from the godly perspective of actual infinity, and this is one of the objections that you can raise against the framework that I have just described, that it is not really a potential infinity if we consider the semantics of what is true in the limit from this godly perspective of taking a look at all models and saying what is true in the limit. It should somehow be evaluated like from locally from those finite models, at least in some sense, right? So let's assume that n is accessible from M if M is a submodel of n. And remember, we have relational language. Right, so for in our FM domain, this boils down to for nm and nn to be in the accessibility relation boils down to having n not greater than n. And now we define what we call modal semantics for finite points of the FM domain. So if we have an atomic formula, then the definition is standard. The clauses for Boolean connectives are standard as well. But there is a difference when we come to the quantifiers. So we say that so if we have a class of finite models, K, then at a given point of this class of finite models, we say that the sentence, there exists an x such that phi of x is modally true or is M true if there is an accessible from M element of the class of finite models K and an element of this accessible universe N such that it is M true in this greater model, still in this class of finite models, in this greater point of the FM domain, that phi of A holds over there. Right? So there is a difference that we say that the sentence there exists an x of phi of x is not true if there exists an object in the universe of M such that phi holds of it, but if there could be more things as to satisfy the property phi, right? There could be means that it is possible to have such a world, possible from the perspective of the world M. It is possible to have an object satisfying the property phi, still with respect to the semantics that we call modal, right? So we do not assume anymore that the satisfaction relation at finite points of the FM domain is usual Tarskian standard definition, but we give it the potentialist flavor. And by the model SL theory, so by the model theory of what is true in the limit in such an FM domain, we take those sentences that are true from some moment on in the model sense, right? So by the class of finite models K, we simply take again the FM domain and the standard model of natural numbers. NKs are still the finite points in our FM domain. So in a sense, the ontology of the model doesn't change. We still have exactly the same objects as structures where we evaluate the sentences of our language, but we evaluate them in a different way. And we evaluate them modally, and we take all those sentences that are true in the limit in the model sense, where the difference between the model sense and the standard sense is that here we have this accessibility relation that influences the way we evaluate quantifiers. Okay. And an example here is that, for example, the sentence stating that there exists the greatest number is, as we said, true in the limit in the standard FM domain semantics, in the standard SL semantics for FM domains, but it is not modally true, right? It is not the case that in the limit the sentence will be modally true, because as you can, I think I don't have it at the slide, but it is also an easy exercise, but you can easily see the reason why this is the case. To modally have this sentence true in the limit, you would have to have that from some moment on. It is the case that you are always, it is always the case that you are able to see a larger point in the FM domain with a particular member of it, such that it would modally be true that this particular member will be greater than all y's, but this is still a quantifier that occurs in the sentence that still has to be evaluated modally. So this particular number A that would supposed to be the greatest element would have to be greater than all the substitutions of y in the greater points in the FM domain. So that is the reason why this will never become an element of the model SL theory of the FM domain. And actually, having the same ontology, but and having the potentialistic finitistic semantics, we still can regain, at least as a kind of an idealization, the arithmetical theory that we would like. So the theorem is that the modal SL theory of the FM domain of natural numbers is simply the true arithmetic. And the reason for that is that finite points are submodels of n. So we use the fact that we consider the relational language here, the quantifier-free formulas are preserved in a point, and it also is closely related to what I just said about the sentence stating that there exists the maximal element, that existentially quantified sentences are true in the standard model if they have a finite witness, and this finite witness belongs to some finite point. And in the model semantics, we actually give justice to that, right? And at this point, that if you have a finite element of a finite point, if you're in your FM domain, this has to be the witness to your model sentences. So one might okay. Before now I want to demonstrate in this modified SL FM framework how do Yablo sequences behave. But if you have a question, what's the difference then if you take this kind of SL theory of finitism? I will get back to that at the end. But before that, let me get to Yablo sentences here. If we take the FM domains in the model interpretation, then actually, assuming that you would have the weakest possible interpretation of the truth predicate for the Yablo sentences in the model SL theory of your FM domain, where, oh, I didn't define the FM domain with Yablo, but FM domain with Yablo is the FM domain for truth, where you additionally have the existence of Yablo sentences in your SL theory. So if you have the Yablo disquotation in your modal SL theory of the finite model domain that knows about Diablo sentences, then actually y of n still then y of n still fail. So they still fail in the limit, or SL fail modally, but then there is actually no FM domain such that would have Yablo disquotation. So this is a kind of a inconsistency result for the model SL theories of the FM domains. And the reason it is an inconsistency result is that you cannot have them that they are false in the limit, and you still have those FM domains where you could have those disquotations satisfied. I mean, you cannot have a theory that has Yablo disquotation, right? And the reason is as follows: suppose you have such an FM domain, then actually you know that they by the theorem that I didn't actually prove here, but you know that they are that they fail in the limit modally, which means exactly that. By the semantics, for any you don't have a point from which they hold. So for n or all n and for all l, there will be something greater in which they modally fail with respect to the kth point of your FM domain. Then unraveling the content of the Yablo sentence, you would still have that for any n and for any l, there is actually p greater than l and a greater than m, such that in the pth point of the FM domain, y of a is under the scope of the truth predicate modally. Then by the Yablo disquotation, this would mean that you have the same thing about y of a, but then if you simply take n and l equal to 0, then you allegedly have that there exist numbers greater than 0, such that for anything greater than p, in the qth point of the finite FM domain by the content of the y of a, you have that for any x greater than a, y of x is not true. And then when you pick a witness that is greater than 0, allegedly, then it would mean that y of a is actually in the MSL theory by the definition of the semantics again, and this gives you a contradiction, right? So you actually cannot have the T schemes for the Yablo sentences in any FM domain. So in a sense, the paradox strikes back. So the dialectics here is as follows. Maybe a way to handle the paradox is to use this finitistic approach to arithmetic that is in the market, and that seems to explicate the notion of potential infinity. Oh yes, hooray! Then all the Yablo sentences are false in the limit. This is like something that should happen if you buy finitism. But well, this finitism is kind of, unconvincing, because you have those very, very dubious arithmetical consequences of the theory of this entire framework. Okay, let's change the framework, because indeed it is possible, especially if it is supposed to explicate the notion of potential infinity. Oh yeah, now the semantics looks believable. We have that it is arithmetically what we would like it to be, even if we want to have that the theory of infinite structure of natural numbers is supposed to be some kind of idealization. But wait, well, then the paradox strikes back. The sequence of Yablo sentences is contradictory again if we assume any kind of behavior of truth predicate on it. So the paradox comes back, and it is not explained away by the appeal to finitistic ideas anyway, right? So to sum it up, the local arithmetical disquotation and local Yablo disquotation, if we add them to our theory, they are consistent but only omega inconsistent. And we know that if we added omega rule or if we added uniform Yablo disquotation, we would have the inconsistency that seems to be there if we reason in the vague natural language. If we take the SL semantics of FM domains, then all the Yablo sentences are false, and the SL theory of such an FM domain is consistent but omega inconsistent. However, the SL theory of the FM domain of natural numbers itself is already omega inconsistent. We can regain arithmetic by changing semantics in a modal way. However, then adding the local Yablo disquotation gives us inconsistency. So you don't anymore need strong assumptions concerning the truth predicate, or you don't need strong infinitary rules of reasoning to be able to say that yes, Yablo sequence is paradoxical. It is paradoxical already with those weak assumptions within the finitistic framework. So now is the point where I will end the discussion of the Yablo paradox itself, and I wanted to devote a couple of minutes to the modal approach to finitism itself, but I need to ask you whether I have 5 to 10 minutes for that, or I should end here and give you some time for questions first.
I'd say go ahead.
Okay, thank you so much. So one might ask, we've got the situation with the Yablo paradox somehow clear, to some extent maybe unsatisfactory, but there is a perspective under the things are the way that they should be, in a sense that it should be the case, as it is with the liar sentence, that adding the disquotation principle for the liar sentence gives us an inconsistency. So it should be the case that the sequence of Yablo sentences gives us a genuine, true contradiction, not some omega contradiction. But then somebody might ask, okay, if you have this believable approach to finitism, then I am entitled to ask, why would you even bother and simply not go ahead to the usual, let's call it actualistic infinitary approach to arithmetic, and why even bother if it gives you the same theory? Isn't it only the syntactic sugar, this entire finitistic approach, or this explication of potential infinity, if your theory in your set of sentences that are supposed to be true in the limit is exactly the same thing as true arithmetic? What's the point? Well, doesn't it mean that when you get this potentialist language, you are simply cheating, and what you are really doing, you are giving the semantics of the standard model, and what's less finitistic than that, right? Why isn't it actually an version of somebody might call it actualism in the sheep's clothing? Our response to that is to make a kind of a thought experiment and consider the second order language of arithmetic, right? So take a relational second order language, keep the model semantics at each initial segment, and keep the formulas to range over the power set of each finite point, and then the set of formulas that belong to the MSL theory will already be different from those that are true in the standard model. So essentially the response will be that, well, yes, on the first order level, you don't see yet the difference between the theory of sentence. You don't see the difference between the set of sentences that are true in the limit in the FM domain and simply the theory of natural numbers, but you will see that on the second order level. And what is more, it is good that it is the second order level at which you see the difference between those two. And the fact that you don't see the difference on the first order level is actually good, because it means that it's actually good as well, because it means that you can keep a kind of a finitistic interpretation of arithmetic of natural numbers, and say that it is simply parlance of the actual infinity or of the standard model is a kind of an idealization from our computational, combinatorial, or call it whatever, experience or combinatorial operations that we have with finite objects. But since the theory that we get from considering this the finite objects, if we consider them in a potentialistic way, gives you the same theory, then it means that this idealization of talking about the infinite model of arithmetic is vindicated. I mean, it's legitimate. We can still do it. We just need to remember that it is only an idealization. But in contrast to the framework that I described previously, we don't have this idealization used in the first place. We don't have the fact that we take all the collection of the finite models and simply evaluate them standardly, right? And the difference will be visible, but in order to be able to see it, you have to move to the second order language. And to describe it, we simply take the power set of the finite segments of the natural numbers, and we add a natural clause for existential second order quantification to the definition of our model semantics. So we say that additionally, at a given finite point, together with the power set of this finite point, the existential second order statement phi of x is true if and only if there is something large and some witness in this larger finite point such that it modally satisfies phi of a. So exactly the same, but for sets instead of numbers. And we additionally extend the definition of the MSL theory for the standard second order models of arithmetic in the obvious way. We still have that for k not greater than n, k is a submodel, and k is a submodel of nn. And what we have, yeah, we shouldn't call it n. This is something that we should perhaps change. What I denote here by n2 is simply the second order standard model of arithmetic. So they just forget about n2 in this sense, right? So this is something that can lead to the confusion. But what we have that psi is in the MSL theory of the FM domain of the second order version of the standard model, if and only if it is simply true in the standard model together with the second order universe consisting of finite sets of natural numbers. Right, so in here it is quite different from the standard second order, from the theory of the standard second order model of arithmetic, right? Where you have the family of finite subsets of natural numbers, then the second order theory of such a structure will be quite different from the theory of the full second order natural number structure. So the second order theories of arithmetic and model finitistic arithmetic are quite different. And the way that we'd like to read those results concerning those second and first order theories under the MSL semantics and under standard semantics give us the following philosophical conclusions: that when you take this potentialist model semantics in the second order version, this is the place in which you capture the finitistic ontology of the FM domains. And it seems okay that the level at which you capture the ontology of the entire class of objects that you consider as the universe for your framework is at a second order level. It is, you know, similar to where you have second order logic and set theory in a sense. It is only on the level of second order theory that you can see certain ontological constructs or ontological bricks of the world that your framework happens at. And at the first order level, this model semantics, as I said, actually gives justice to justifies why we can be philosophically finitistic and still be allowed to consider the infinitistic idealization of natural numbers legitimate, and we can explain why we keep proving things about infinite structures of natural numbers and other more complicated things, while trying to say that still on a fundamental philosophical level, it seems that there are, finitely many objects that we can experience, or that we can compute with, or that we can combinatorially interact with, and there is a way to explain that. And it also means that if you have a finitistic approach to first order arithmetic, it doesn't have to be revisionary, right? Because some people say that when you present the explication of the notion of potential infinity and some weak versions of finitism, then they think that you want to revise mathematics. So the answer is no. Exactly by the fact that you can get the same theory as the standard theory of arithmetic. This means that this approach is not to revise anything, and it is just to philosophically explain the way that from the finite we get to the infinite while we consider arithmetic in some sense. But yet there is a difference between the second order theory of natural numbers in the potentialistic sense and the second order theory of the standard model of arithmetic in the usual sense, which means that you are actually not reducing your entire framework to hidden version of actualism while giving your first order model semantics for finitism. But of course, somebody might say, and this is something I don't have a good reply to, rather than saying that this second order model SL theory of N is just to illustrate the difference between semantics and ontology. But somebody might say that, yeah, that for the second order theory, potentialistic model's second order theory of what is true in the limit, that's very, very restrictive if you have only finite sets of natural numbers over there. But then, my initial reply that I would like to philosophically still work out is that as in many contexts, the second order theories of anything should be treated instrumentally as ways to perhaps shed some light on something, and not as something that should not be restrictive, because we, after all, reason and work with the first order resources. And that's the conclusion that I would like to end up with. And here we can see a sequence of finite books, perhaps that each says that all the ones behind it are actually false, and then the last one might be right or not. And that depends on what exactly this Ghent library has in those books, which now I'm not fully sure of. And the guy on the right here is exactly Rafał Urbaniak, whom I announced that will be present in this way or another today. And yeah, the last thing I have is the references. So thank you. That's all from me for now.
Thank you, Michał. We have maybe a few minutes for questions. So, any questions?
Yeah, I could ask something else if nobody else wants to jump in. This is about your SL semantics, which I hadn't seen before. I was just wondering, it reminded me a bit of like sort of ultra filter, only it's clearly it's not some kind of ultra filter, but maybe if you look at it's a very strong truth condition. From some point on, it always is to remain true. So that's more like just the filter, the filter of co-finite sets. So I wonder if there is some connection between the SL semantics and some sort of filter, not like an ultra filter construction, but it's a non-ultra filter construction, just using the filter of co-finite sets. Are you familiar with any connection along these lines?
Yes, I am. However embarrassing as it is, I now don't remember the exact formulation of the theorem, but there is a paper by Michał Krynicki, Konrad Zdanowski, and Jerzy Tomasik that actually exactly explores the filter formulation of the semantic of the SL semantics. And I don't remember the main theorem that gives this characterization, but I am happy to provide later the exact reference and recall the theorem. But yes, there and as far as I know, that there has been this one paper in this direction.
Well, then this allows the potential for some sort of extension here. If a connection has already been made, if it's already been developed, this notion of filter semantics, then you could pick a different filter, which is still not an ultra filter.
That's an idea to have truth with respect to not a cofinite filter, but to some other notion of largeness. Yep. Thanks.
Yeah, I can chime in with a question or two.
Okay.
The second question is, sorry, my video doesn't work. My second question is there a connection with this work and Parikh's paper on feasibility and ultrafinitism?
Is it a question if I see any connection or?
Yeah, or have you?
No, I haven't. No, and I haven't thought about it actually.
Okay. The second question is, have you guys, has anyone looked at when infinitary languages came out and miscible sets and all that? One of the things we did was take a look at Gödel's theorem, Ross's theorem, and extend them to set theories and admissible sets and whatnot. Is anything like that been done with, say, the Yablo sequence or other parts of this work?
As far as I know, there is one paper by some group in Italy concerning topological interpretation of Yablo's Yablo's paradox. But I thought it was I didn't see a large potential theory over there when I first encountered it. But also I am not sure whether you would. I mean, there is a more general phenomenon and question here that when you think of those axiomatic theories of truth, which are over there, and there is a large and beautiful work being done about them with respect to the language of arithmetic, with respect to the higher order languages such as, I don't know, language of set theory, some of the results are simply said to transfer from the context of arithmetic, but some not necessarily. And I think that there is still an open need for having a systematic theory of axiomatic theories of truth over languages such as set theory in essence. And other than that, I don't have any like specific or particular results concerning Diablo sequences over set theory.
Thank you.
Michał, and I have a question. Maybe you did address it because at the end everything was done rather quickly. But I understand there was this issue of first order versus second order, and what I was thinking about in the case of those finite approximations, this distinction, although so strong for for infinite domains, for finite domains, seems a little tricky, because if you are in a small domain, and if you move up in this, feasibility in your family of models, then what is second order in a small model, if you go high enough, through coding may become first order, actually does become first order, because the larger model knows everything about smaller model together with all of its subsets. So perhaps there is some translation of first order phenomena, second order phenomena into first order. In the limit, they all somehow melt together. So did you think about that? And one of the things I was thinking about, to somehow model this phenomenon of explosion of cardinalities, that perhaps in your feasibility relation you may impose some condition of how large this larger model is supposed to be, where you're looking for an example of something.
No, we haven't thought about it, but I do get the idea. that if you, I mean, for a given class of sentences of this or that complexity, to have a witness, you have to go this or that up in the FM domain to find the witness or something like that, right? Is that
right? That's
okay.
the idea.
Thank you. Thank you.
And I see Attar has a question. It's in the
Attar asked the question if it is right away inconsistent. So it seems to me that the answer to Attar's question, let me read it loud, but I need to get to chat. Yeah, so I will read out what Attar wrote. Can one formulate the Yablo notion without the truth predicate? That is, define a Yablo formula as any arithmetical formula y of x with the property that PA proves for all x, y of x, if and only if, for all z greater than x, not y of z. And the question is, does PA simply prove that no such arithmetical formula exists? No, actually, it proves that, as far as I know, I hope not to make a mistake, but I think that it proves that it exists, and that actually, even if you don't have the truth predicate, so let's, instead of y, let's consider any predicate f of any sort. Then you can still have a consistent theory and a non-standard model for that. And I have to check that, but it seems to me that it follows from one of the Ketland's papers, that this paper of Ketland in 2005, when it analyzes Yablo's paradox, it proves the consistency of a given theory and its omega inconsistency as a special case of a more general consistency, where instead of Yablo formula, you have some arbitrary formula with only some mild restrictions to it. So it seems to me that it doesn't, I think it doesn't have to be inconsistent right away. I think it still can be consistent, but omega inconsistent. But that I will check and let you know.
Okay. Any more questions? Well, if not, then let's thank Michał one more time. And let me remind you.
Thank you so much, and thank you for all the suggestions and remarks. This is great.
Thank you, Michał. And so we have program now, MOPA program almost until the end of May. So stay tuned for announcements and Vika's email. Okay, thank you.